Dear listener, today I want to show you that it's also possible to create thermal models without any Gerber drill files, etc., just by importing a bitmap, whatsoever the origin of the bitmap is, Visio, Paint, whatever you want. This is part of a heater, the shape of a thin foil with conductor material in black and insulator in white. And this piece of foil is mounted or placed on a substrate in between the substrate and the cover, and we now have to replace this placeholder heater by the contour of the bitmap content. So first of all, we have to define the in quote layer stack. The cover is supposed to be 0.5 millimeters thick, the substrate glass 2 millimeters, and the heater is the result of a silk screen printing with some special paste of conductive material. To create the model, we have to import the bitmap, which is simply to add the file, and to expose, which means reading the Gerber file and creating computational nodes. This is done very fast. And here we have it. We don't have drill files, we don't have placement files. What we have to add are positions or points of voltage in, voltage out, or current in and current out. I prepared using a 12 volt source and a 0 volt sink, which means the current will flow from high voltage to low voltage using this geometry. And the next step is to run the case. Before we run, we have to think about the environmental conditions, default at 20 degrees, and we just have to calculate. In the log window, you see the progress of the results. The first step is to calculate the voltage drop or the potential distribution in the traces, and of course the current density and the joule heating. This is already done. We create a heating of almost 50 watts, and the question is, what is the temperature equivalent to this 50 watts given the ambient conditions, given the conductivity of the materials and the geometry and the thickness, etc. The voltage and the current are calculated. That's quite fast, and we can view the voltage distribution. It's looking quite homogeneous, but indeed it isn't homogeneous. There is a sort of asymmetry with respect to the central line. We have more traces there, less traces there. If we watch the current density, we see the current density in red, which is high current here, and less current there in orange, and the direction of the current. Let's have a look at the temperature. Still calculating in an iterative process. We just have to be patient for a minute. Temperature is now calculated. The 50 watts which we create in the trace are completely leaving the setup by top and bottom phase. We plot the temperature and we view the temperature results. This is the temperature distribution in the heater foil. Maximum temperature is almost 140 degrees, which could be a little bit too much. But of course the parameters can be changed and recalculated. We see the effect of the asymmetry of the situation. There is less current in that part, also less heating and lower temperature. We see some corner effect. We can see the temperature in the substrate. and we can see the temperature in the cover. We can also check by numbers. In the report file, we have a listing of the input data and the results, the created heat, the heat flux balance, and of course the min-max temperature, etc. This calculation can also be done in a transient mode, so to say a heating curve to the temperature at some final time, or we can apply a cyclic power dissipation on and off states and follow the transient heating. Thank you for watching. You are welcome to take a test installation.